Welcome learners for the lecture 15 of a differential geometry. Today we discuss about theorem 4. If ds represented the elements of the area PQRS on the surface, ds equals to h du dv. Then what is the proof of this area will be considering to the form elements of area. Let the parametric coordinates of a PQ, R and S be the uv, u plus del uv, u plus del u, v plus del v and u v plus del v respectively. Okay, means a p considering a first, q considering second, r considering third and s considering four. Okay, when del u del v are a small portion, pqrs is a parallelogram. Now pq equals to oq minus op means r u plus del v, v minus r uv. Okay, using approximate Taylor expansion we get it PQ equals to RUV plus del R upon del U into del U minus RUV, that is a R1 considering as a del U. In similar manner, PS equals to R2 del V using du dv instead of a del U del V. We have to the vector area of a parallelogram is considering R1 du into R2 dv will be considering, so that to the area will be considering R1 du into R2 dv equals to mod of a R1 into R2 du dv means a mod will be considering as a h du dv. This is the theorem will be considering as a respectively. Hence prove that h du dv gives the elementary area of a ds on this surface. For getting as an example, find E, F, G and H for the paraboloid x equals to u, y equals to v, z equals to u square minus v square. Okay, what is the solution of the paraboloids? Has the position vector r equals to u v, u square minus v square. Hence r1 equals to 102 u, r2 equals to 01 minus 2v, that is the E equals to r1 into r2 equals to 1 plus 4u square. F equals to considering r1 into r2, that is a minus uv, and g equals to r1 into r2 1 plus 4 v square. Further r1 cross r2 equals to minus 2u plus 2v and 1. Hence h equals to mod of r1 cross r2 equals to square root of 4u square plus 4v square plus 1, which is also equals to square root of eg minus f. Okay, they will be given. Next topic will be considering direction coefficient on a surface. Okay, this is a 10 point will be considering. In the case of a curve in the space, we will able to obtain to the moving traits of a mutually perpendicular unit vector t and b with the help of the able to express any vector points to the curve linearly in the terms of a t and b. Then throws cannot to the analogous of the t and b to the point trying to the similar points p on the surface. Let r equals to ruv be the equation of a surface and p be the any point on the surface. Then we get it to the form r1 into r2 on the tangent parametric curve, v equals to constant and u equals to also constant passing through the point of the P, then N be the surface of a normal will be given to the perpendicular to the form of a surface. Then R1 cross R2 is not equals to 0. Neither R1 nor R2 can be scalar multiple of the other, so that R1 and R2 are the linearly independent. Further, air cannot be scalar multiple of the R1 of a R2. For if N equals to A R1, then N dot N equals to A R1 and n equals to 0, which is absurd since it will be given 1 equals to 0. This at any points on the surface, three linearly independent form will be given n, r1 and r2. Hence every point of a vector a through the point p can be expressed uniquely as a linear combination of a three vectors n, r1 and r2. Thus there exists unique scalar an, lambda and mu considered such that a equals to an capital N plus lambda r1 plus mu r2. This expressed to the form as a point p. Sum of two vector an n is a normal surface will be given and lambda r1 plus mu r2 lying on the tangent of this. Then we obtain a dot n equals to an n dot n. Considering when solving to the equation is called as a normal coefficient of a. From this is easily to the tangent lying on this form. The vector lambda r1 plus mu r2 lying on the tangent of the plane is called as a tangential part of A, and lambda mu are called as a tangential component of A. This component lambda and mu depend only on the tangential part, not getted as any normal surface of this form. Okay, this is the basic concept will be given as a tangential and normal form of the equation.